Close your eyes for a moment and imagine the deepest darkness you've ever known. Not the gentle darkness of your bedroom at night, with street lights painting soft rectangles on your walls, or even the profound quiet of a forest clearing under a moonless sky. No, imagine a darkness so complete, so absolute, that light itself cannot escape its embrace. A darkness that bends the very fabric of reality, where time moves like honey, and space curves back upon itself like a cosmic spiral staircase leading nowhere and everywhere at once. This is the realm of the black hole, perhaps the most mysterious, beautiful, and terrifying concept in all of human knowledge. Tonight, as we settle into this gentle journey through time and space, we'll discover how these cosmic enigmas went from being merely the wild imaginings of brilliant minds to becoming the cornerstone of our understanding of the universe itself. But our story doesn't begin with Einstein or Hawking, as you might expect. It doesn't start in the gleaming laboratories of the 20th century or with the massive telescopes that pierce the cosmic veil. No, our tale begins much earlier, in the mind of a country priest in the English countryside, on a quiet evening in 1783 when the world was simpler, slower, and lit only by candles and stars. The Reverend's dark vision. The year is 1783. King George III still rules over Britain, though he has recently lost his American colonies. The French Revolution is still 6 years in the future. Mozart is composing his symphonies, and the world runs on wind, water, and the strength of horses. In this world, where the fastest anyone has ever traveled is perhaps 30 miles per hour on horseback, a quiet man named John Michell sits in his study in the village of Thornhill, Yorkshire. The Reverend John Michell is not your ordinary country priest. Yes, he tends to his flock on Sundays, delivering sermons in the stone church that has stood in Thornhill for centuries. But when Monday morning comes and the last echoes of the church bells fade across the Yorkshire dales, Michell transforms into something else entirely, one of the most brilliant natural philosophers of his age. Picture him now, in the amber glow of candlelight, his study filled with the quiet sounds of a winter evening, the soft hiss of the fire in the hearth, the gentle scratching of his quill pen across parchment, the distant lowing of cattle in the fields beyond his window. On his desk lie the tools of his trade: brass instruments for measuring angles and distances, thick leather-bound books filled with the mathematical work of Newton, and page after page of calculations in his own careful handwriting. Michell has been thinking about light, not the warm, familiar light that dances from his candle flame, but light as Newton described it, as tiny particles, what we might call photons today, racing through space at incomprehensible speed. Newton's great work, the Principia, sits open before him, its pages worn from countless readings. Newton had shown that everything in the universe pulls on everything else with an invisible force called gravity. The apple falls from the tree because Earth pulls it down. The moon circles Earth because Earth's gravity holds it in its orbit. The planets dance around the sun for the same reason. But Michell's mind goes further. If gravity can pull on apples and moons and planets, he wonders, could it not also pull on light itself? After all, Newton himself believed light was made of tiny particles. And if light is made of particles, those particles must have mass, however small. And if they have mass, then gravity must affect them. The mathematics that flow from his pen that winter evening are deceptively simple. Using Newton's own equations, he calculates what would happen if you gathered enough mass together in one place. At first, the calculations describe familiar things: a planet massive enough to hold on to a thick atmosphere, a star so large that its surface gravity is stronger than Earth's. But as the mass grows in his calculations, something remarkable happens. At a certain point, a point he can calculate precisely, the gravitational pull becomes so strong that even light itself cannot escape its embrace. The escape velocity, as we call it today, exceeds the speed of light itself. Michel has just mathematically described what we now call a black hole, though he uses a different term. He calls them dark stars. If the semi-diameter of a sphere of the same density as the Sun were to exceed that of the Sun in the proportion of 500 to 1, a body falling from an infinite height towards it would have acquired at its surface greater velocity than that of light, and consequently, supposing light to be attracted by the same force in proportion to its vis inertia with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. Read those words again, slowly. This quiet country priest has just predicted the existence of objects so massive that light itself cannot escape them. In 1783, more than a century before Einstein will publish his theory of relativity, Jean Michel has glimpsed the cosmic abyss. But here's what makes this moment even more extraordinary. Michel doesn't stop at mere theoretical speculation. With the practical mind of an experimental philosopher, he proposes how such dark stars might be detected. If you can't see them directly, for they emit no light, you might still observe their effects on nearby stars. If a dark star orbited with a normal star, the visible star would appear to dance alone in space, pulled by an invisible partner. It's a method we still use today to detect black holes. As the candle burns lower in his study, Michel finishes his calculations and sets down his quill. Outside, the Yorkshire countryside sleeps under a blanket of stars, the same stars that have watched over England for thousands of years. But inside this quiet rectory, something has changed. Humanity has taken its first step toward understanding that the universe contains mysteries far stranger than anyone had dared to imagine. Michel presents his work to the Royal Society in 1783, but his dark stars are so far ahead of their time that they barely ripple the waters of scientific thought. The idea seems too strange, too removed from ordinary experience to be taken seriously. It will be filed away, forgotten, waiting patiently in the archives of human knowledge for the right moment to resurface. But seeds once planted have a way of growing in their own time, and the seed that Jean Michel planted that winter evening in Yorkshire will eventually grow into one of the most profound and beautiful theories in all of science. Fabric of space and time. Our story now jumps forward more than a century to a very different world. The year is 1905, and the pace of human life has accelerated beyond anything John Mitchell could have imagined. Steam trains thunder across continents at 60 miles per hour. Electric lights illuminate the great cities of Europe and America. The first automobiles sputter and roar through cobblestone streets, frightening horses and delighting children. In this rapidly changing world, in the Swiss Federal Institute of Technology in Zurich, a young man with wild, dark hair and penetrating eyes is about to revolutionize our understanding of reality itself. His name is Albert Einstein, and he is 26 years old. Einstein has been thinking about light, just as John Mitchell did more than a century earlier. But Einstein's approach is different. Where Mitchell accepted Newton's view of light as particles, Einstein has become convinced that light is something far stranger, a wave that somehow doesn't need a medium to travel through, unlike sound waves or water waves. This leads him to a startling conclusion. The speed of light is the same for everyone, everywhere, no matter how fast they're moving. Picture Einstein in his small apartment in Bern, where he works as a patent clerk. The mundane nature of his day job, reviewing applications for new inventions, gives his mind the freedom to wander into the deepest mysteries of existence. In the evenings, he sits at his kitchen table, covered with sheets of paper filled with equations, while his wife Mileva tends to their young son, Hans Albert. The mathematics that flow from Einstein's pen are revolutionary. If the speed of light is constant, he realizes, then space and time themselves must be flexible, elastic, capable of stretching and contracting. When you travel very fast, close to the speed of light, time slows down for you relative to everyone else. Space contracts. Mass increases. These aren't just mathematical curiosities, they're fundamental properties of reality itself. This is the special theory of relativity, and it shatters our intuitive understanding of the universe. But Einstein doesn't stop there. Over the next 10 years, he extends his theory to include gravity, and this is where our story of black holes truly begins to accelerate. Einstein's general theory of relativity, published in 1915, describes gravity not as a force that pulls objects toward each other, but as a curvature in the fabric of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll marbles near it, they will spiral inward, not because the bowling ball is pulling them, but because they're following the curved surface of the sheet. In Einstein's universe, massive objects like stars and planets curve space-time around them, and what we experience as gravity is simply matter following these curves. It's a picture of reality so beautiful and so strange that even Einstein himself sometimes struggled to believe it could be true. The equations of general relativity are stunningly elegant, but fiendishly difficult to solve. Einstein himself manages to find solutions only for the simplest cases. But within months of publishing his theory, other mathematicians and physicists begin exploring its implications. One of them is Karl Schwarzschild, a German astronomer and physicist serving on the Russian front during World War I. Picture Schwarzschild in his makeshift quarters on the Eastern Front in early 1916. Around him, the Great War rages with unprecedented fury. Artillery shells scream overhead, machine guns rattle in the distance, and men die in numbers that boggle the mind. But in this hell of mud and blood and poison gas, Schwarzschild finds solace in mathematics. Working by lamplight in his tent, he tackles Einstein's field equations, searching for exact solutions. Within just 2 months of Einstein's publication, Schwarzschild finds one. His solution describes the curvature of space-time around a perfectly spherical, non-rotating mass. It's an idealized case. No real star is perfectly spherical or completely non-rotating, but mathematics often begins with such idealizations, and profound truths can emerge from them. As Schwarzschild works through his calculations, something curious appears in the equations. At a certain distance from the central mass, a distance that depends on how much mass is concentrated at the center, the mathematical description of space-time seems to break down. The curvature becomes infinite, time appears to stop, space itself seems to tear apart. Schwarzschild doesn't fully understand what he's found. Working in the trenches of a terrible war, with limited resources and no one to discuss his work with, he simply notes this mathematical peculiarity and moves on. He has no way of knowing that he has just rediscovered Jean Michel's dark stars, now encoded in the fundamental geometry of space and time itself. Tragically, Schwarzschild never sees the full implications of his work. Just weeks after mailing his solution to Einstein, he dies of an autoimmune disease contracted on the Russian front. He is only 42 years old, but his mathematical legacy will outlive him by centuries. The distance at which Schwarzschild's solution breaks down comes to be called the Schwarzschild radius. For our Sun, it's about 3 kilometers. For Earth, it's about 9 millimeters. These might seem like abstract numbers, but they represent something profound. The size an object would need to be compressed to in order to become a black hole. Einstein himself is troubled by Schwarzschild's solution. The mathematical breakdown at the Schwarzschild radius seems to suggest that general relativity might be flawed, incomplete. For decades, most physicists, including Einstein, will assume that real stars could never collapse to such extremes. Nature, they believe, must have some mechanism to prevent such catastrophic collapse. They are wrong, but it will take almost 50 years for anyone to understand why. The Chandrasekhar limit. The scene shifts now to India, to the port city of Madras in 1928. The British Raj is at its height.
though cracks are beginning to show. Mahatma Gandhi's independence movement gains momentum with each passing year. In the universities and colleges of India, a new generation of brilliant minds is emerging, young people who will soon reshape our understanding of the cosmos. Among them is a 19-year-old student named Subramanian Chandrasekhar. Friends call him Chandra. And even at this young age, his intellect burns with a fierce, pure light. He has just completed his undergraduate degree at Presidency College in Madras, studying physics and mathematics with an intensity that both amazes and worries his professors. Chandra comes from a family where intellectual achievement is treasured above all else. His uncle, C.V. Raman, will soon win the Nobel Prize in Physics for his work on the scattering of light. The dinner conversations in Chandra's household are filled with discussions of quantum mechanics, stellar structure, and the latest discoveries from the great observatories of the world. In the summer of 1928, Chandra receives news that will change his life. He has been awarded a scholarship to study at Cambridge University in England. The prospect fills him with excitement and terror in equal measure. Cambridge is the University of Newton and Darwin, the place where some of the greatest minds in history have walked. But it also means leaving behind everything familiar, his family, his culture, his homeland, to venture into a world where he will be one of the few Indians among the English elite. As summer turns to autumn, Chandra prepares for the long sea voyage to England. In those days before commercial aviation, the journey from India to Britain takes weeks, sailing through the Suez Canal and across the Mediterranean. It's a time for reflection, for reading, for thinking about the problems that fascinate him most. Chandra has become obsessed with stars, not their beauty or their poetry, but their physics. How do they shine? What keeps them from collapsing under their own enormous weight? How do they live? And how do they die? These questions have been puzzling astronomers since the dawn of science, but now, with the new tools of quantum mechanics and relativity theory, they might finally have answers. As his ship crosses the Arabian Sea, Chandra spends long hours on deck, looking up at the vast canopy of stars visible in the southern sky. The tropical heat makes sleeping below decks unbearable, so, like many passengers, he brings his bedding up to the open air. There, with the gentle rolling of the ship and the whisper of wind in the rigging, he reads and calculates and dreams. The book that occupies most of his attention during this voyage is Arthur Eddington's The Internal Constitution of the Stars, published just 5 years earlier. Eddington, one of the most brilliant astrophysicists of his generation, has proposed a radical new understanding of how stars work. At their cores, he suggests, the temperature and pressure are so extreme that atoms are stripped of their electrons, creating a sea of atomic nuclei and free electrons. The pressure of this electron gas, governed by the strange new laws of quantum mechanics, is what holds the star up against the crushing weight of gravity. But as Chandra reads Eddington's work, a troubling question begins to form in his mind. Eddington's theory works beautifully for most stars, including our own sun. But what happens to really massive stars? What happens when a star has accumulated so much mass that even the quantum pressure of electrons isn't enough to hold it up? Night after night, as his ship sails across the Indian Ocean, Chandra works through the mathematics. The calculations are complex, involving the strange new physics of quantum mechanics combined with Einstein's special relativity. But gradually, an answer emerges, an answer so shocking that Chandra can hardly believe it himself. There is a limit, he realizes, a specific mass above which no white dwarf star can exist. If a star ends its life with more than about 1.4 times the mass of our own sun concentrated in a sphere the size of Earth, the quantum pressure of electrons simply cannot provide enough support. The star must continue to collapse. But collapse to what? Chandra's calculations cannot say. All they can tell him is that there is no known force in physics powerful enough to stop the collapse. The star must shrink and shrink and shrink until what? Until it becomes something that has never been seen, never been imagined, something for which physics has no name. By the time Chandra's ship docks in London in the autumn of 1930, Chandra has calculated what will later be known as the Chandrasekhar limit. He has shown that some stars must inevitably collapse beyond the point where normal matter can exist. Without knowing it, he has taken the crucial step toward understanding black holes. But Chandra is just 20 years old, a foreign student in a strange land, about to challenge one of the most revered figures in British astronomy. Arthur Eddington, the very man whose book inspired Chandra's voyage of discovery, will become his greatest opponent, dismissing his work as stellar buffoonery. The stage is set for one of the most dramatic conflicts in the history of science.
The Great Debate. Cambridge in 1930 is a place of ancient stones and modern ideas, where medieval courtyards echo with discussions of quantum mechanics and relativity. The university that produced Newton now hosts some of the most brilliant scientific minds of the 20th century. Among them, Arthur Eddington stands like a colossus, the man who confirmed Einstein's general relativity by observing the bending of light during a solar eclipse, the scientist who first understood how stars shine. Into this rarefied atmosphere comes young Chandra, clutching his calculations about stellar collapse. He is assigned to work under Eddington's supervision, and initially, the great man seems pleased with his brilliant young protege. Eddington has always been fond of Indian students, and Chandra's mathematical prowess is undeniable. For several years, Chandra develops his ideas quietly. He refines his calculations, explores their implications, begins to understand that he has discovered something fundamental about the fate of massive stars. But he is cautious, respectful of hierarchy, careful not to challenge his mentor too directly. The breakthrough comes in 1934. Chandra has been invited to present his work at a meeting of the Royal Astronomical Society in London, a tremendous honor for such a young scientist. The topic of his talk is the highly collapsed configurations of a stellar mass. In the formal language of scientific discourse, he will argue that stars above a certain mass must collapse indefinitely, creating objects unlike anything previously imagined in astronomy. Picture the scene, the venerable halls of the Royal Astronomical Society, filled with the elite of British astronomy. Gas lamps cast a warm glow over rows of distinguished faces, professors emeritus with white whiskers, middle-aged researchers at the height of their careers, and young students hoping to catch a glimpse of the future of their field. Chandra, now 24 but looking younger, stands at the lectern with his carefully prepared notes. His voice is clear and precise as he walks through his mathematics, explaining how the pressure of degenerate electrons can support a star against gravity only up to a certain mass limit. Beyond that limit, he explains that there is no known force that can prevent continued gravitational collapse. He says, the star will continue to radiate away energy until it has shrunk to a point mass, or what we might call a black hole in space. It is, as far as we know, the first time this term is used in a scientific context, though it won't become common for another 30 years. The audience listens with growing unease. What Chandra is describing sounds more like science fiction than science fact. A star that collapses to a point? An object from which light cannot escape? It seems to violate everything they understand about how nature works. But the real shock comes when Chandra finishes his presentation and takes his seat. Arthur Eddington, the grand old man of British astronomy, rises to respond. What follows is one of the most dramatic confrontations in the history of science. I think there should be a law of nature to prevent a star from behaving in this absurd way, Eddington declares, his voice carrying the full weight of his authority. The stellar theory he has developed over decades, he argues, shows that stars must find some way to achieve equilibrium. The idea of indefinite collapse, he suggests, is not just wrong, but philosophically offensive. The room falls silent. In the polite world of British academia, such direct confrontation is almost unheard of.
Here is the most respected astrophysicist in Britain publicly dismissing the work of a young Indian student as stellar buffoonery.
The star has to go on radiating and contracting until, I suppose, it gets down to a few kilometers radius when gravity becomes strong enough to hold in the radiation and the star can at last find peace, Eddington says with heavy sarcasm. Dr. Chandrasekhar had got this result before, but he has rubbed it in his last paper. And when discussing it with him, I felt driven to the conclusion that this was almost a reductio ad absurdum of the relativistic degeneracy formula. Various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in this absurd way. The young Chandra sits in stunned silence as laughter ripples through the audience. His life's work, his most profound insight into the nature of the universe, has just been dismissed as absurdity by the very man he most admires. The humiliation is complete and public. In the aftermath of this confrontation, Chandra finds himself professionally isolated. Eddington's opposition effectively kills interest in his work among British astronomers. Job opportunities dry up. His ideas are ignored or dismissed. The young man who had sailed from India with such high hopes now faces a choice: abandon his revolutionary ideas and pursue more conventional research, or continue down a path that seems to lead only to professional suicide. Chandra chooses exile. In 1937, he accepts a position at the University of Chicago, leaving Britain behind. For the next 3 decades, he will build a distinguished career studying other aspects of astronomy and physics. But the work that would have earned him immortality, his discovery of the inevitability of black holes, remains forgotten, buried under the weight of Eddington's authority. It will be 30 years before the scientific community recognizes that Chandra was right and Eddington was wrong. 30 years before anyone understands that the absurd objects Chandra predicted are not only real, but are among the most important phenomena in the universe. When that recognition finally comes, it will be too late to undo the damage to a brilliant career, too late to give Chandra the credit he deserved, at the time he deserved it. But the universe, as we are about to discover, is under no obligation to conform to our sense of what is reasonable or absurd. Reality, it turns out, is far stranger than even the most imaginative scientists dared to believe. The nuclear furnace. While Chandra's revolutionary ideas about stellar collapse languish in academic exile, other scientists are making discoveries that will eventually confirm his predictions in spectacular fashion. The 1930s and 1940s are decades of incredible progress in physics, driven partly by the urgent needs of a world at war, but also by the pure intellectual excitement of exploring new frontiers. In laboratories around the world, physicists are beginning to understand the source of stellar energy, the nuclear fusion that powers the stars. It's a story that begins with the work of Hans Bethe, a brilliant German physicist who fled Nazi Germany and found refuge at Cornell University in upstate New York. Picture Bethe in his office at Cornell in 1938, working through the nuclear reactions that might occur in the core of a star. The temperature there is about 15 million degrees Celsius, hot enough to strip electrons from atoms and smash atomic nuclei together with tremendous force. In these cosmic furnaces, Bethe realizes hydrogen nuclei can fuse together to form helium, releasing enormous amounts of energy in the process. The mathematics are elegant and precise. 4 hydrogen nuclei, each with a mass of about 1 atomic mass unit, combine to form 1 helium nucleus, with a mass of about 4 atomic mass units. But, and here is the key, the helium nucleus is actually slightly less massive than the 4 hydrogen nuclei that formed it. The missing mass has been converted to energy, following Einstein's famous equation, E equals mc squared.
Even though the mass difference is tiny, less than 1%, the speed of light squared is an enormous number. The energy released by converting just 1 kilogram of hydrogen into helium is equivalent to burning 20,000 tons of coal. In the core of our Sun, 600 million tons of hydrogen are converted to helium every second, and our Sun is considered a rather average, unremarkable star. This fusion process, Bethe shows, can keep a star like our Sun shining for about 10 billion years. It's a span of time almost impossible to comprehend, longer than the current age of the Earth, longer than complex life has existed on our planet. Yet it is not forever. Eventually, every star must run out of fuel. For stars like our Sun, the end comes relatively peacefully. As the hydrogen in the core is exhausted, the star swells to become a red giant, eventually puffing off its outer layers to leave behind a hot, dense core called a white dwarf. These white dwarfs, no larger than Earth, but containing the mass of a star, slowly cool and fade over billions of years. They represent the final fate of most stars in the universe. But what about massive stars? Stars with 10, 20, 50 times the mass of our Sun. For these stellar giants, the story is far more dramatic. As massive stars age, they develop the structure of a cosmic onion. Hydrogen fuses to helium in the core. When the hydrogen is exhausted, the core contracts and heats up until helium begins fusing into carbon and oxygen. When the helium runs out, the core contracts again, and carbon begins fusing into heavier elements, neon, silicon, sulfur. Each successive stage burns faster and at higher temperatures. Hydrogen fusion might last millions of years. Silicon fusion lasts only days. Finally, inevitably, the star begins producing iron in its core. Iron is special. It's the most stable nucleus in nature. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires energy input. Iron is the end of the nuclear road. Picture the final moments of a massive star. In its core, an iron sphere about the size of Earth but containing more mass than our Sun grows larger with each passing second. The temperature is billions of degrees. The pressure is beyond anything we can recreate in terrestrial laboratories. And then, in less than it takes to blink your eyes, the core can no longer support its own weight. The collapse is catastrophic. In a fraction of a second, matter at the density of atomic nuclei, the densest form of matter known, is compressed to even higher densities. Protons and electrons are crushed together to form neutrons. The collapsing core bounces off this ultra-dense neutron matter and rebounds outward as a shock wave that tears through the outer layers of the star. What we see from Earth is a supernova, an explosion so brilliant that for a few weeks, a single star can outshine an entire galaxy of 100 billion stars. The energy released in those few seconds is more than our Sun will produce in its entire 10 billion year lifetime. But what happens to the core? In some cases, it settles into a new equilibrium as a neutron star, a sphere only about 20 kilometers across but containing more mass than our Sun. These neutron stars are so dense that a teaspoon of neutron star material would weigh as much as Mount Everest. But there is a limit to how much mass a neutron star can contain, just as Chandra had calculated decades earlier for white dwarf stars. Above about 3 solar masses, even the pressure of degenerate neutrons cannot halt the gravitational collapse. The matter continues to contract past the point where atoms can exist, past the point where even neutrons can survive, past any known form of matter. What remains is exactly what John Michell had imagined in his Yorkshire rectory almost 2 centuries earlier, what Carl Schwarzschild had glimpsed in the trenches of World War I, what Chandra had calculated during his voyage to England, an object so dense that nothing, not even light itself, can escape from its gravitational pull. By the 1960s, theoretical physicists finally understood that such objects were not just mathematical curiosities, but inevitable consequences of stellar evolution. The universe, they realized, must be populated with these dark, invisible remnants of dead stars. But proving they actually existed would require a new generation of telescopes and a new way of thinking about astronomical observation. After all, how do you see something that emits no light?
Searching for the invisible. The story of actually finding black holes is a detective story unlike any other in science. How do you search for something that cannot be seen? Something that reveals its presence only through its gravitational influence on the space and matter around it. It's like trying to find an invisible person by watching how others react to their presence, detecting an absence rather than a presence. The key insight came from John Mitchell's original 18th century prediction. If a black hole orbited with a normal star, the visible star would appear to dance alone in space, pulled by an invisible partner. This dance would be revealed by careful study of the star's motion and the light it emits. In the early 1960s, a new generation of astronomical instruments began to reveal the universe in wavelengths of light invisible to human eyes. Radio telescopes, first developed during World War II for radar research, opened up entirely new vistas of cosmic exploration. X-ray detectors, lifted above Earth's atmosphere by rockets and satellites, began to map the high-energy universe. It was in this new X-ray sky that astronomers found their first real clues to the existence of black holes. In 1964, a small rocket launched from White Sands Missile Range in New Mexico detected an intense source of X-rays in the constellation Cygnus, the Swan. The source was designated Cygnus X1, the first X-ray source found in that constellation. Initially, no one suspected that Cygnus X1 might be a black hole. X-ray astronomy was so new that any discovery was surprising. But as more sensitive instruments were developed and launched, a strange picture began to emerge. Cygnus X1 was not just bright in X-rays, it was variable, flickering and changing in brightness on timescales as short as milliseconds. This was a crucial clue. The rapid flickering meant that the X-ray emitting region had to be very small, no larger than the distance light travels in a millisecond, which is only about 300 kilometers. Yet this tiny region was somehow producing more energy than entire stars. The breakthrough came when optical astronomers managed to identify the visible star associated with Cygnus X1. It was a hot blue supergiant star designated HD 226868, located about 6,000 light-years from Earth. But something very strange was happening to this star. Detailed spectroscopic studies revealed that HD 226868 was moving back and forth along our line of sight with a period of 5.6 days, as if it were orbiting around an invisible companion. The mathematics of orbital mechanics allowed astronomers to calculate the mass of this unseen object. It contained at least 10 times as much matter as our Sun, yet produced no visible light whatsoever. Picture the scene as astronomers around the world began to realize what they had found. In observatories from California to Chile to Australia, telescopes swung toward Cygnus as researchers tried to understand this cosmic enigma. Here was an object more massive than any known neutron star, yet completely invisible. What could it be but the black hole that theorists had predicted? But the story was even more remarkable than a simple invisible companion. The X-rays, astronomers realized, were not coming from the black hole itself. Nothing can escape from a black hole, not even X-rays. Instead, they were coming from an accretion disk, a swirling maelstrom of hot gas spiraling inward toward the black hole's event horizon. The process works like this. The black hole's immense gravity strips material from its companion star. This material doesn't fall straight into the black hole, but instead forms a flat, rotating disk around it. Friction within the disk heats the gas to temperatures of millions of degrees, hot enough to emit copious X-rays. As the gas spirals inward, it gains speed and grows hotter, until in the final moments before crossing the event horizon, it reaches temperatures of billions of degrees and shines with the brightness of millions of suns.
It's a process of spectacular violence and beauty. Matter that has existed peacefully in the outer layers of a star for millions of years is suddenly caught in an inexorable spiral toward oblivion. As it falls, it releases gravitational potential energy at an efficiency no terrestrial power plant could match. The conversion of matter to energy as material falls into a black hole is about 10 times more efficient than nuclear fusion, the process that powers the stars themselves. The discovery of Cygnus X1 marked the beginning of black hole astronomy. Throughout the 1970s and 1980s, astronomers found more and more X-ray sources that displayed similar characteristics: rapid variability, association with invisible massive companions, evidence of hot accretion disks spiraling inward toward unseen gravitational monsters. Each discovery built the case that these objects were indeed the black holes predicted by theory. But perhaps more importantly, they revealed that black holes were not just cosmic curiosities, but active participants in the universe's ongoing story. They were not passive endpoints of stellar evolution, but dynamic engines that could influence their surroundings across vast distances. As astronomers peered deeper into space with ever more sophisticated instruments, they began to realize that black holes might be even more common and more important than anyone had imagined. The universe, it seemed, was not just populated with these invisible monsters. In many ways, it was shaped by them. The supermassive surprise. While astronomers were still marveling at their discovery of stellar mass black holes like Cygnus X1, observations were accumulating that hinted at something even more extraordinary. At the centers of many galaxies, including our own Milky Way, something massive and invisible seemed to be lurking in the darkness. The first hints came from radio astronomy. In the 1950s and 1960s, radio telescopes began detecting incredibly powerful sources of radio waves from the deep cosmos. These sources, initially called radio stars, turned out to be something far more exotic than their name suggested. When optical telescopes were pointed at the positions of these radio sources, they revealed objects that looked like stars but had very peculiar properties. These quasi-stellar objects, or quasars as they came to be known, were among the most distant objects in the observable universe. Yet, despite their enormous distance, some were billions of light-years away, they outshone entire galaxies. A single quasar could emit more energy than 100 billion normal stars. What could possibly generate such prodigious amounts of power? The answer, when it finally emerged, was almost too incredible to believe. Quasars, astronomers realized, were powered by supermassive black holes, objects containing millions or billions times the mass of our Sun, feeding on vast quantities of gas and dust in the centers of distant galaxies. Picture the scene at Palomar Observatory in California in the late 1960s. The great 200-inch Hale telescope, then the largest in the world, sweeps across the night sky as astronomers work to understand these mysterious quasars. The photographic plates they develop in the observatory's darkroom reveal points of light that look deceptively ordinary, yet represent some of the most violent and energetic phenomena in the universe. Martin Schmidt, a Dutch-American astronomer working at Caltech, makes the crucial breakthrough when he analyzes the spectrum of a quasar designated 3C273. The spectrum shows familiar patterns of hydrogen emission, but shifted dramatically toward the red end of the spectrum. This redshift indicates that 3C273 is receding from us at an enormous velocity, about 16% the speed of light, placing it at a distance of about 2.5 billion light-years. At such a vast distance, for 3C273 to appear as bright as it does, it must be intrinsically incredibly luminous. Schmidt's calculations show that this single object is emitting more energy than 1,000 billion suns. The numbers seem almost meaningless. How can the human mind grasp such scales of power and distance?
But the story becomes even more remarkable when astronomers realize that quasars are variable. Like the X-ray sources that led to the discovery of stellar mass black holes, quasars brighten and dim on relatively short timescales, sometimes changing dramatically in just a few months or years. This variability provides another crucial clue to their nature. The rapid changes mean that the energy-producing region must be relatively compact. Even traveling at the speed of light, it takes time for a signal to cross large distances. If a quasar varies in brightness over a period of 1 year, the emitting region cannot be much larger than 1 light-year across. Yet this tiny region, tiny on cosmic scales, is producing more energy than entire galaxies spanning 100,000 light-years. Only one known mechanism could produce such incredible power from such a compact region: matter spiraling into a supermassive black hole. Just as with stellar mass black holes, the energy comes not from the black hole itself, but from the superheated accretion disk of material falling toward the event horizon. But the scales involved are almost beyond comprehension. A supermassive black hole powering a quasar might consume the equivalent of several Earth masses every minute. The accretion disk around such an object could be larger than our entire solar system, yet hot enough to outshine billions of stars. Jets of particles and radiation, accelerated to nearly the speed of light by the black hole's magnetic field, shoot outward from millions of light-years, creating the radio sources that first revealed these objects to human observation. As the 1970s progressed, astronomers began to understand that quasars represented an early, violent phase in the evolution of galaxies. In the early universe, when galaxies were young and gas-rich, their central black holes grew rapidly by consuming vast quantities of material. This feeding frenzy powered the quasars we observe at great distances and therefore far back in time. But what about nearby galaxies? What about our own Milky Way? If supermassive black holes were common features of galactic centers, shouldn't we be able to find evidence for one much closer to home? The search for a black hole at the center of our own galaxy became one of the great quests of late 20th century astronomy. Unlike the distant quasars, our galaxy's center is hidden behind clouds of dust and gas that block visible light. But infrared and radio waves can penetrate this cosmic fog, revealing the hidden heart of the Milky Way. What they found there was extraordinary. At the exact center of our galaxy, radio telescopes detected a compact source called Sagittarius A*, pronounced A star. This object appeared to be associated with something very massive yet invisible. Infrared telescopes revealed stars in the galactic center moving at incredible speeds, some reaching velocities of thousands of kilometers per second as they looped around the invisible object. The orbital mechanics were undeniable. The stars near the galactic center were orbiting something containing about 4 million times the mass of our Sun, concentrated in a region smaller than the orbit of Neptune. It could only be a supermassive black hole, not currently active like the distant quasars, but lurking quietly at the heart of our home galaxy. This discovery revolutionized our understanding of galaxy formation and evolution. Apparently, nearly every large galaxy harbored a supermassive black hole at its center. These cosmic monsters played a crucial role in regulating star formation throughout their host galaxies, sometimes stimulating it through their powerful jets and outflows, sometimes suppressing it by heating and dispersing the gas from which new stars form. The universe, astronomers realized, was not just populated with black holes, it was organized around them. From stellar mass objects formed in supernova explosions to supermassive giants that grew along with their host galaxies, black holes were fundamental features of cosmic architecture.
But even as astronomers were making these remarkable discoveries about black holes through their effects on surrounding matter, a parallel revolution was taking place in theoretical physics. Scientists were beginning to understand that black holes were not just astrophysical curiosities, but laboratories for exploring the deepest laws of nature, the intersection of gravity, quantum mechanics, and thermodynamics.
The story begins with the work of Roy Kerr, a New Zealand mathematician who in 1963 found a solution to Einstein's field equations that described a rotating black hole. This was a monumental achievement. Einstein's equations are notoriously difficult to solve exactly, and Kerr's solution was only the second exact solution ever found, after Schwarzschild's non-rotating case from 1916. Kerr's rotating black hole, now called a Kerr black hole, is probably what most real black holes in the universe actually look like. Since most stars rotate, we would expect the black holes formed from their collapse to rotate as well. And what Kerr discovered was that rotation changes everything about how a black hole behaves. Picture a Kerr black hole in your mind's eye. It's no longer a perfect sphere, but is flattened at the poles and bulging at the equator like a spinning top. Its rotation drags space-time itself around with it, creating a region called the ergosphere, where nothing, not even light, can remain stationary relative to distant observers. Inside the ergosphere, everything must rotate along with the black hole, caught in the grip of twisted space-time. But Kerr's solution revealed something even more remarkable. Unlike the Schwarzschild black hole, which has a single event horizon, the Kerr black hole has two, an outer horizon and an inner horizon. And at the very center, where the Schwarzschild solution predicts a point of infinite density called a singularity, the Kerr solution suggests something different, a ring singularity. This ring singularity has bizarre properties that challenge our understanding of causality and time travel. Theoretical calculations suggest that if you could somehow survive the journey through both event horizons, which you can't for reasons we'll explore, you might find yourself in a region where the normal flow of time breaks down completely. Some solutions to the equation suggest you could travel backwards in time, or even into parallel universes. These possibilities are almost certainly unphysical. Nature probably has ways of preventing such paradoxical situations, but the mere fact that they appear in the mathematics hints at how strange and profound the physics of black holes really is. As physicists delved deeper into black hole theory during the 1960s and 1970s, they discovered that these objects had properties that seemed almost biological. Black holes, they found, could grow by consuming matter and energy. They could merge with other black holes, creating larger ones. They could even, under certain circumstances, split apart. The mathematical framework describing these processes was developed by physicists like Stephen Hawking, Roger Penrose, and Kip Thorne. Their work revealed that black holes obey strict conservation laws. When two black holes merge, the area of the resulting black hole's event horizon is always greater than the sum of the areas of the original two horizons. This area theorem seemed to suggest that black holes could only grow, never shrink. But then in 1974, Stephen Hawking made a discovery that stunned the physics community and launched a revolution in our understanding of black holes, quantum mechanics, and the nature of information itself. He had been thinking about what happens when you combined quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, with general relativity's description of black holes. Quantum mechanics tells us that empty space is not really empty, but is filled with virtual particle pairs that constantly pop into existence and annihilate each other in unimaginably short time intervals. Usually, these quantum fluctuations have no observable effects, because the particle pairs exist for such brief moments and in perfect balance. For every particle, there's an antiparticle and they cancel each other out. But near the event horizon of a black hole, Hawking realized something different happens. If a virtual particle pair appears right at the event horizon, one particle might fall into the black hole, while the other escapes to infinity. The escaping particle becomes real, carrying away a tiny amount of energy.
To conserve energy, the black hole must lose mass to compensate. In effect, the black hole gradually evaporates by emitting what we now call Hawking radiation. The implications of this discovery are staggering. First, it means that black holes are not perfectly black. They actually glow with a faint thermal radiation. Second, and more importantly, it means that black holes can shrink and eventually disappear completely.
The story begins with the work of Roy Kerr, a New Zealand mathematician who in 1963 found a solution to Einstein's field equations that described a rotating black hole. This was a monumental achievement. Einstein's equations are notoriously difficult to solve exactly, and Kerr's solution was only the second exact solution ever found, after Schwarzschild's non-rotating case from 1916. Kerr's rotating black hole, now called a Kerr black hole, is probably what most real black holes in the universe actually look like. Since most stars rotate, we would expect the black holes formed from their collapse to rotate as well. And what Kerr discovered was that rotation changes everything about how a black hole behaves. Picture a Kerr black hole in your mind's eye. It's no longer a perfect sphere, but is flattened at the poles and bulging at the equator like a spinning top. Its rotation drags space-time itself around with it, creating a region called the ergosphere, where nothing, not even light, can remain stationary relative to distant observers. Inside the ergosphere, everything must rotate along with the black hole, caught in the grip of twisted space-time. But Kerr's solution revealed something even more remarkable. Unlike the Schwarzschild black hole, which has a single event horizon, the Kerr black hole has two: an outer horizon and an inner horizon. And at the very center, where the Schwarzschild solution predicts a point of infinite density called a singularity, the Kerr solution suggests something different: a ring singularity. This ring singularity has bizarre properties that challenge our understanding of causality and time travel. Theoretical calculations suggest that if you could somehow survive the journey through both event horizons, which you can't for reasons we'll explore, you might find yourself in a region where the normal flow of time breaks down completely. Some solutions to the equation suggest you could travel backwards in time, or even into parallel universes. These possibilities are almost certainly unphysical. Nature probably has ways of preventing such paradoxical situations. But the mere fact that they appear in the mathematics hints at how strange and profound the physics of black holes really is. As physicists delved deeper into black hole theory during the 1960s and 1970s, they discovered that these objects had properties that seemed almost biological. Black holes, they found, could grow by consuming matter and energy. They could merge with other black holes, creating larger ones. They could even, under certain circumstances, split apart. The mathematical framework describing these processes was developed by physicists like Stephen Hawking, Roger Penrose, and Kip Thorne. Their work revealed that black holes obey strict conservation laws. When two black holes merge, the area of the resulting black hole's event horizon is always greater than the sum of the areas of the original two horizons. This area theorem seemed to suggest that black holes could only grow, never shrink. But then in 1974, Stephen Hawking made a discovery that stunned the physics community and launched a revolution in our understanding of black holes, quantum mechanics, and the nature of information itself. He had been thinking about what happens when you combine quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, with general relativity's description of black holes. Quantum mechanics tells us that empty space is not really empty, but is filled with virtual particle pairs that constantly pop into existence and annihilate each other in unimaginably short time intervals. Usually, these quantum fluctuations have no observable effects, because the particle pairs exist for such brief moments and in perfect balance. For every particle, there's an antiparticle and they cancel each other out. But near the event horizon of a black hole, Hawking realized something different happens. If a virtual particle pair appears right at the event horizon, one particle might fall into the black hole, while the other escapes to infinity. The escaping particle becomes real, carrying away a tiny amount of energy.
To conserve energy, the black hole must lose mass to compensate. In effect, the black hole gradually evaporates by emitting what we now call Hawking radiation. The implications of this discovery are staggering. First, it means that black holes are not perfectly black. They actually glow with a faint thermal radiation. Second, and more importantly, it means that black holes can shrink and eventually disappear completely.
A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero. It would take longer than the age of the universe for such a black hole to evaporate. But a black hole with the mass of a mountain would be about as hot as the Sun's surface. And a black hole with the mass of an asteroid would be hot enough to emit X-rays and gamma rays, eventually exploding in a final burst of energy as it evaporated completely. This discovery led to what physicists call the information paradox, one of the deepest unsolved problems in theoretical physics. When matter falls into a black hole, it carries information with it. Information about its quantum state, its history, its properties. If the black hole eventually evaporates through Hawking radiation, what happens to that information? The laws of quantum mechanics seem to require that information be conserved. It cannot be created or destroyed, only transformed. But if information disappears into a black hole and the black hole later evaporates, the information seems to vanish from the universe entirely. This apparent contradiction has puzzled physicists for decades and continues to drive research at the intersection of quantum mechanics and gravity. Some physicists propose that the information somehow escapes as the black hole evaporates, encoded in subtle correlations in the Hawking radiation. Others suggest that information is stored at the event horizon itself in a holographic encoding that maintains all the information about what has fallen in. Still others propose that the information paradox reveals fundamental flaws in our understanding of space, time, or quantum mechanics itself. The debate continues, but it has already led to profound insights about the nature of reality. The holographic principle, born from black hole physics, suggests that all the information in a volume of space can be encoded on its boundary, like a hologram that appears three-dimensional but is actually stored on a two-dimensional surface. This idea has revolutionized our thinking about spacetime, suggesting that what we perceive as three-dimensional reality might actually be a projection from a two-dimensional information surface. Black hole physics has also led to discoveries about the fundamental limits of knowledge and computation. The Bekenstein bound, named after physicist Jacob Bekenstein, sets a limit on how much information can be contained in a given region of space. The limit is related to the area of the region's boundary, not its volume. Another hint at the holographic nature of reality. These discoveries have transformed black holes from astronomical curiosities into tools for exploring the deepest questions about the nature of existence itself. They have become laboratories for testing our most fundamental theories, revealing connections between seemingly unrelated areas of physics and pointing toward new paradigms for understanding the universe. But perhaps the most remarkable thing about black hole physics is how it forces us to abandon our everyday intuitions about space, time, and reality. Near a black hole, time runs slower, space is curved, and the boundary between past and future becomes blurred. At the event horizon, time appears to stop entirely from the perspective of outside observers, while falling objects experience it normally. These effects aren't just theoretical curiosities, they're measurable, observable consequences of Einstein's relativistic universe. As we'll see in our final chapters, recent technological advances have allowed astronomers to observe these relativistic effects directly, providing spectacular confirmation of our theoretical understanding. The journey from John Mitchell's dark stars to the recent images of actual black hole event horizons represents one of the greatest intellectual achievements in human history, a testament to our species' ability to understand the universe through reason, mathematics, and careful observation. The Event Horizon Telescope. In the early 21st century, as our understanding of black hole physics matured, a new dream began to take shape in the minds of astronomers. What if we could actually see a black hole? Not just detect its gravitational effects or observe the hot gas spiraling around it, but actually image the event horizon itself.
This dream seemed impossible at first. Black holes are, by definition, black. They emit no light that we can detect. Moreover, even the supermassive black holes at the centers of galaxies are incredibly small when viewed from Earth. The black hole at the center of our own Milky Way, despite containing 4 million times the mass of our Sun, appears smaller in the sky than a golf ball would appear on the Moon. To image such a tiny, dark object would require a telescope with impossible resolution, far beyond anything that could be built as a single instrument. But in the 1990s, astronomers began to dream of a different approach. What if they could link radio telescopes around the world to create a virtual telescope as large as Earth itself?
This technique, called Very Long Baseline Interferometry, or VLBI, had been used successfully for decades to study radio sources with extraordinary precision. By combining signals from telescopes thousands of miles apart, astronomers could achieve angular resolution equivalent to what a single telescope the size of the separation would provide. But applying this technique to image a black hole would push the technology to its absolute limits. The technical challenges were staggering. Radio waves from space arrive at different telescopes at slightly different times, depending on the precise geometry of the observation and the Earth's rotation. To combine these signals coherently, astronomers need to measure these tiny time differences with incredible precision, accurate to billionths of a second. They need atomic clocks at each telescope site, synchronized to better than any timing system ever built. Moreover, the amount of data involved is enormous. Each telescope records the radio waves hitting its antenna with such high time resolution and bandwidth that a single night of observations can generate more data than the Large Hadron Collider produces in a year. This data must be recorded on hard drives and physically shipped to supercomputers for processing. There's simply too much to transmit over the internet. The dream of imaging black holes began to become reality in the early 2000s with the formation of the Event Horizon Telescope collaboration. This international project brought together radio telescopes from around the world, from the Atacama Large Millimeter Array in Chile to the James Clerk Maxwell Telescope in Hawaii, from the IRAM 30-meter telescope in Spain to the South Pole Telescope in Antarctica. Picture the scene during an EHT observing run. At radio observatories scattered across the globe, teams of astronomers and technicians work through the night, battling equipment failures, weather problems, and the thousand small crises that inevitably plague such complex observations. In Chile's Atacama Desert, they work at altitudes where every breath is precious. In Hawaii, they dodge volcanic eruptions. In Antarctica, they endure temperatures that can freeze instruments solid. The coordination required is extraordinary. All the telescopes must observe the same source at exactly the same time, following it as Earth's rotation carries it across the sky. Weather at any site can ruin the observation for everyone. A single equipment failure can compromise data from the entire array. The primary target for these observations was Sagittarius A star, or SGR-A star, the supermassive black hole at the center of our own galaxy. This object offered the best combination of size and proximity, large enough and close enough that its event horizon might just be detectable with the EHT's unprecedented resolution. But SGR-A star presented its own challenges. The galactic center is an incredibly dynamic environment. Gas and dust swirl around the black hole in chaotic patterns, changing from minute to minute. The radio waves from this region must travel through clouds of ionized gas that act like a lens, distorting and blurring the image. It's like trying to photograph a marble at the bottom of a swimming pool while someone creates waves on the surface. For years, the EHT team worked to refine their techniques, add new telescopes to the array, and develop the sophisticated algorithms needed to turn their raw data into actual images. The computational challenges were as daunting as the observational ones. Creating an image from interferometric data is not like developing a photograph. It requires complex mathematical transformations that can take weeks or months of supercomputer time. The breakthrough came in April 2017, when weather conditions around the world aligned perfectly for a series of EHT observations. For 5 nights, telescopes on 6 continents tracked SGR-A star and another target, the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The M87 black hole, designated M87 star, is much more massive than SGR-A star, about 6.5 billion times the mass of our Sun, but also much more distant. But it offered certain advantages as a target. The environment around M87 star is more stable than the chaotic region near SGR-A. The radio emission from its vicinity is steadier, making it easier to image with the techniques available to the EHT.
What followed was 2 years of painstaking data analysis. Teams of scientists around the world worked independently to process the same data, developing different algorithms and techniques to extract images from the radio signals. Only when multiple teams arrived at similar results could the collaboration be confident that they were seeing real features rather than artifacts of their processing methods. The moment of truth came in early 2019. In simultaneous press conferences around the world, a recognition of the truly global nature of the achievement, the EHT collaboration released the first image ever made of a black hole's event horizon. The image showed M87* as a dark shadow surrounded by a bright ring of glowing gas. The shadow was exactly the size and shape predicted by Einstein's general relativity for a black hole of M87*'s mass. The bright ring was the photon sphere, the region just outside the event horizon, where light can orbit the black hole before either falling in or escaping to infinity. For many who saw the image, the first reaction was surprise at how ordinary it looked. After decades of science fiction movies and artistic interpretations, the real thing seemed almost anticlimactic, a fuzzy orange donut against the black of space. But for physicists and astronomers, the image was a triumph beyond their wildest dreams. Here, finally, was direct visual evidence of an event horizon, the point of no return predicted by Einstein's equations more than a century earlier. The shadow's size matched theoretical predictions to within measurement errors. Its circularity confirmed that even M87*'s rapid rotation, it spins at about half the maximum rate possible for a black hole, wasn't enough to significantly distort its shape as seen from Earth. The image also revealed the first direct evidence of the asymmetric brightness pattern around a black hole predicted by relativistic effects. One side of the ring appeared brighter than the other, exactly as expected from the Doppler effect, as gas orbits at speeds approaching the speed of light. 3 years later, in May 2022, the EHT team released an even more remarkable achievement, the first image of Sagittarius A*, the black hole at the center of our own galaxy. This image was much more challenging to produce because of SGR-A*'s variability, but it confirmed that our own galactic center harbors the same kind of object seen in M87*. The success of the Event Horizon Telescope represents one of the greatest technological and scientific achievements of the 21st century. It vindicated more than a century of theoretical work, from Einstein's field equations to Hawking's insights about black hole thermodynamics. It demonstrated that humans can, through ingenuity and international cooperation, push the boundaries of what seems possible. But perhaps most importantly, it marked the beginning of a new era in black hole astronomy. The EHT is continuously being improved, with new telescopes joining the array and new observing techniques being developed. Future observations promise to reveal the dynamics of gas flow around black holes, test Einstein's theory in ever more extreme conditions, and perhaps even provide insights into the information paradox and other deep questions in fundamental physics. The journey from John Mitchell's theoretical dark stars
to the actual images of black hole event horizons spans nearly 250 years of human intellectual achievement. It's a story of persistence in the face of seemingly impossible challenges, of international cooperation transcending political boundaries, and of the power of human curiosity to unlock the deepest secrets of the cosmos. The Symphony of Space-Time. As the Event Horizon Telescope was capturing the first images of black holes, another revolutionary detection method was quietly making history. This story begins not with light or radio waves, but with the fabric of space-time itself, and humanity's first direct detection of the gravitational waves that Einstein predicted a century ago. The story of gravitational wave astronomy is inseparable from the story of black holes, because it was the collision and merger of black holes that provided the first clear gravitational wave signals. To understand this achievement, we must first understand what gravitational waves are and why they're so extraordinarily difficult to detect. According to Einstein's general relativity, massive objects moving through space create ripples in the fabric of space-time itself. These ripples travel at the speed of light, carrying energy away from the system that created them. It's similar to how a stone dropped in a still pond creates water waves that spread outward, except that gravitational waves are waves in the very geometry of space and time. Einstein himself was uncertain whether gravitational waves actually existed or were merely mathematical artifacts of his theory. The waves are incredibly weak. Even the most violent cosmic events produce gravitational waves that stretch and compress space by amounts smaller than 1/10,000th the width of a proton. Detecting such minute distortions seemed impossible with any conceivable technology.
But in the 1960s and 1970s, a new generation of physicists began to dream of doing the impossible. Leading this effort was Rainer Weiss at MIT, along with Kip Thorne at Caltech and Ronald Draver at Glasgow University, later also at Caltech. Their idea was audacious: build laser interferometers sensitive enough to detect the passage of gravitational waves. The concept is elegantly simple in principle. Set up two identical laser beams traveling down perpendicular arms of equal length. If a gravitational wave passes through, it will stretch space in one direction while compressing it in the perpendicular direction. This will cause one laser beam to travel a slightly longer path and the other a slightly shorter one. When the beams are recombined, the tiny difference in path length will show up as a change in their interference pattern. Simple in principle, but devilishly difficult in practice. The path length changes that gravitational waves produce are so small that every conceivable source of noise and vibration must be eliminated. The laser mirrors must be isolated from ground vibrations, thermal fluctuations, quantum noise, and even the pressure of photons themselves. The entire system must operate in ultra-high vacuum to prevent air molecules from interfering with the laser beams. The engineering challenges were so severe that it took decades to develop the necessary technology. Test facilities were built and rebuilt, new techniques for isolating the mirrors from vibrations were developed, more powerful lasers were designed, advanced materials were crafted to create mirrors with unprecedented reflectivity. Finally, in the 1990s, the U.S. National Science Foundation approved funding for the Laser Interferometer Gravitational Wave Observatory, LIGO. The project would build two identical detectors, one in Hanford, Washington, and another in Livingston, Louisiana. Each detector would have arms 4 kilometers long, with laser beams bouncing back and forth hundreds of times to increase the effective path length. The construction of LIGO was an engineering marvel. Each site required perfectly straight vacuum chambers stretching for miles across the landscape. The mirrors, among the most perfectly polished objects ever created, had to be suspended as pendulums to isolate them from ground vibrations. The entire system had to be computer-controlled to maintain alignment to unprecedented precision. LIGO began operations in 2002, but the first generation of detectors was not sensitive enough to detect gravitational waves. For nearly a decade, the collaboration refined their techniques and improved their instruments,
all while searching for signals in data that contained only noise. It was a period of enormous frustration and dedication. Hundreds of scientists and engineers working on a project that might never succeed. The breakthrough came with advanced LIGO, an upgraded version of the detector that began operations in September 2015. The improvements were dramatic. The new detectors were about 10 times more sensitive than the original LIGO, able to detect gravitational wave strains as small as 10 to the negative 21. On September 14, 2015, at 9:50:45 UTC, both LIGO detectors simultaneously recorded a signal unlike anything ever seen before. The gravitational wave strain rose from noise, swept upward in frequency over a fraction of a second, then vanished. The pattern was exactly what theorists had predicted for two black holes spiraling into each other and merging. Picture the scene as LIGO scientists around the world received alerts about this detection. Many initially assumed it was a test signal. The collaboration routinely injected fake signals into the data stream to test their analysis procedures. But as the hours passed and no one claimed responsibility for injecting the signal, the realization dawned that they might have detected real gravitational waves. The analysis that followed was painstaking and thorough. Every possible source of error was investigated. The signal was compared with theoretical predictions from computer simulations of black hole mergers. Alternative explanations were considered and ruled out. Only after months of careful study did the collaboration announce their discovery to the world. The source of the gravitational waves, designated GW150914, was determined to be the merger of two black holes approximately 1.3 billion light-years away. One black hole contained about 36 times the mass of our Sun, the other about 29 solar masses. When they merged, they formed a single black hole of about 62 solar masses. The missing 3 solar masses, equivalent to the mass of our entire Sun, had been converted to gravitational wave energy in accordance with Einstein's E=mc². The violence of this event is almost impossible to comprehend. In the final moments before merger, the two black holes orbited each other at speeds exceeding 100,000 kilometers per second, about 1/3 the speed of light. The gravitational wave power radiated away was greater than the combined light output of all stars in the observable universe. Yet from our perspective on Earth, this cosmic catastrophe registered as a distortion of space smaller than 1/10,000th the width of a proton. The detection of GW150914 opened an entirely new window on the universe. For the first time, humans had detected gravitational waves, confirming a prediction Einstein made a century earlier, and opening a new field of astronomy that observes the cosmos through space-time itself rather than electromagnetic radiation. But in the 1960s and 1970s, a new generation of physicists began to dream of doing the impossible. Leading this effort was Rainer Weiss at MIT, along with Kip Thorne at Caltech and Ronald Draver at Glasgow University, later also at Caltech. Their idea was audacious: build laser interferometers sensitive enough to detect the passage of gravitational waves. The concept is elegantly simple in principle. Set up two identical laser beams traveling down perpendicular arms of equal length. If a gravitational wave passes through, it will stretch space in one direction while compressing it in the perpendicular direction. This will cause one laser beam to travel a slightly longer path and the other a slightly shorter one. When the beams are recombined, the tiny difference in path length will show up as a change in their interference pattern. Simple in principle, but devilishly difficult in practice. The path length changes that gravitational waves produce are so small that every conceivable source of noise and vibration must be eliminated. The laser mirrors must be isolated from ground vibrations, thermal fluctuations, quantum noise, and even the pressure of photons themselves. The entire system must operate in ultra-high vacuum to prevent air molecules from interfering with the laser beams. The engineering challenges were so severe that it took decades to develop the necessary technology. Test facilities were built and rebuilt. New techniques for isolating the mirrors from vibrations were developed. More powerful lasers were designed. Advanced materials were crafted to create mirrors with unprecedented reflectivity. Finally, in the 1990s, the U.S. National Science Foundation approved funding for the Laser Interferometer Gravitational Wave Observatory, LIGO. The project would build two identical detectors, one in Hanford, Washington, and another in Livingston, Louisiana. Each detector would have arms 4 kilometers long, with laser beams bouncing back and forth hundreds of times to increase the effective path length. The construction of LIGO was an engineering marvel. Each site required perfectly straight vacuum chambers stretching for miles across the landscape. The mirrors, among the most perfectly polished objects ever created, had to be suspended as pendulums to isolate them from ground vibrations. The entire system had to be computer-controlled to maintain alignment to unprecedented precision. LIGO began operations in 2002, but the first generation of detectors was not sensitive enough to detect gravitational waves. For nearly a decade, the collaboration refined their techniques and improved their instruments, all while searching for signals in data that contained only noise. It was a period of enormous frustration and dedication. Hundreds of scientists and engineers working on a project that might never succeed. The breakthrough came with advanced LIGO, an upgraded version of the detector that began operations in September 2015. The improvements were dramatic. The new detectors were about 10 times more sensitive than the original LIGO, able to detect gravitational wave strains as small as 10 to the negative 21. On September 14, 2015, at 9:45 UTC, both LIGO detectors simultaneously recorded a signal unlike anything ever seen before. The gravitational wave strain rose from noise, swept upward in frequency over a fraction of a second, then vanished. The pattern was exactly what theorists had predicted for two black holes spiraling into each other and merging. Picture the scene as LIGO scientists around the world received alerts about this detection. Many initially assumed it was a test signal. The collaboration routinely injected fake signals into the data stream to test their analysis procedures. But as the hours passed and no one claimed responsibility for injecting the signal, the realization dawned that they might have detected real gravitational waves. The analysis that followed was painstaking and thorough. Every possible source of error was investigated. The signal was compared with theoretical predictions from computer simulations of black hole mergers. Alternative explanations were considered and ruled out. Only after months of careful study did the collaboration announce their discovery to the world. The source of the gravitational waves, designated GW 150914, was determined to be the merger of two black holes approximately 1.3 billion light-years away. One black hole contained about 36 times the mass of our Sun, the other about 29 solar masses. When they merged, they formed a single black hole of about 62 solar masses. The missing 3 solar masses, equivalent to the mass of our entire Sun, had been converted to gravitational wave energy in accordance with Einstein's E equals mc squared. The violence of this event is almost impossible to comprehend. In the final moments before merger, the two black holes orbited each other at speeds exceeding 100,000 kilometers per second, about 1/3 the speed of light. The gravitational wave power radiated away was greater than the combined light output of all stars in the observable universe. Yet from our perspective on Earth, this cosmic catastrophe registered as a distortion of space smaller than 1/10,000th the width of a proton. The detection of GW 150914 opened an entirely new window on the universe. For the first time, humans had detected gravitational waves, confirming a prediction Einstein made a century earlier, and opening a new field of astronomy that observes the cosmos through space-time itself rather than electromagnetic radiation.
Since that first detection, LIGO and its international partners, including the Virgo detector in Italy and CAGRA in Japan, have detected dozens of gravitational wave events. Most have been black hole mergers, but the array has also detected collisions between neutron stars and even the merger of a neutron star with a black hole. Each detection has revealed new insights about black hole physics. The mergers show that stellar mass black holes can grow to much larger sizes than previously expected. They reveal that black hole spins can be aligned or misaligned with their orbital motion, providing clues about how binary black hole systems form and evolve. They've even provided new tests of Einstein's general relativity in the strong field regime, confirming the theory's predictions with unprecedented precision. Perhaps most remarkably, gravitational wave astronomy has revealed that black hole mergers are common events in the universe. Advanced LIGO detects roughly one black hole merger per week, suggesting that throughout the cosmos, these violent events are occurring constantly, sending ripples through spacetime that carry information about some of the most extreme physics in nature. The success of gravitational wave astronomy represents a triumph of human persistence and ingenuity. It required developing technology at the very limits of what's possible, international collaboration on a massive scale, and decades of patient work by hundreds of scientists and engineers. The payoff has been a completely new way of studying the universe, one that has already revealed phenomena that could never have been discovered through traditional astronomy. As we look to the future, even more sensitive gravitational wave detectors are being planned. Space-based interferometers like LISA will be able to detect waves from supermassive black hole mergers across the universe. Third-generation ground-based detectors will be sensitive enough to observe black hole mergers throughout cosmic history. These future observations promise to answer fundamental questions about black hole formation, galaxy evolution, and the nature of gravity itself. They may even provide new insights into the information paradox and other deep mysteries of black hole physics. The detection of gravitational waves from black hole mergers represents humanity's first direct observation of Einstein's curved spacetime in action. It's an achievement that would have seemed like science fiction to John Michell contemplating his dark stars in 18th century Yorkshire, yet it flows directly from the theoretical foundations he helped establish nearly 2.5 centuries ago. Black holes and the fate of information. As we near the end of our cosmic journey, we turn to one of the most profound and puzzling questions in all of physics, the black hole information paradox. This puzzle sits at the intersection of quantum mechanics and general relativity, challenging our most fundamental assumptions about the nature of reality itself. The story begins, as so many stories in black hole physics do, with Stephen Hawking. In 1975, a year after his discovery of black hole evaporation, Hawking made an even startlinger claim. Not only do black holes evaporate through the emission of thermal radiation, he argued that the information that falls into them is destroyed forever when the black hole finally disappears. To understand why this claim was so shocking, we need to appreciate one of the fundamental principles of quantum mechanics, information conservation. In the quantum world, information, the complete description of a system's quantum state, cannot be created or destroyed. It can be scrambled, encoded in complex ways, or spread across multiple particles, but the total amount of information in the universe must remain constant. This principle had been tested countless times in laboratory experiments and had never been violated. It seemed to be as fundamental as the conservation of energy or electric charge. Yet Hawking's analysis suggested that black holes routinely violated information conservation on a cosmic scale. Picture the paradox. Imagine you have a book, say a copy of Shakespeare's complete works. You throw this book into a black hole. According to classical general relativity, the book's information is now trapped forever behind the event horizon. But according to Hawking's calculation, the black hole will eventually evaporate completely through quantum radiation, leaving behind only a bath of thermal photons that carry no information about what fell in. Where did the information in Shakespeare's sonnets go? Hawking argued that it was simply destroyed, erased from the universe when the black hole evaporated. But this seemed to violate one of the most basic principles of quantum mechanics. The scientific community was divided. Some physicists, following Hawking's lead, argued that black holes represented a genuine exception to information conservation, that general relativity's strong gravitational fields could indeed destroy quantum information.
Others insisted that information must somehow escape from black holes, perhaps encoded in subtle correlations in the Hawking radiation that were too complex for current theory to describe. The debate raged for decades. It wasn't merely an academic dispute about esoteric physics. It went to the heart of our understanding of reality. If information could be destroyed, then the quantum mechanical description of reality might be fundamentally incomplete. If information always survived, then our understanding of black holes and general relativity needed major revision.
One of the most creative attempts to resolve the paradox came from Leonard Susskind at Stanford University. In the 1990s, Susskind proposed what he called the holographic principle, the idea that all the information about the interior of a region of space could be encoded on its boundary like a hologram. Applied to black holes, the holographic principle suggests that information falling through the event horizon is simultaneously encoded on the horizon's surface. From the perspective of an outside observer, the information never actually enters the black hole, but remains smeared across the event horizon. The black hole's interior, from this viewpoint, might not even exist as an independent reality, but could be a holographic projection of information stored on the surface. This idea seemed bizarre and counterintuitive. How could the same information exist both inside and outside the black hole? Wouldn't this lead to paradoxes about the nature of reality itself? Susskind's answer was even more radical. He suggested that the paradox revealed something fundamental about the nature of space and time. Perhaps space-time itself wasn't fundamental, but was an emergent property of more basic information theoretic structures. Perhaps what we think of as the interior of a black hole was actually a holographic reconstruction based on information stored at the boundary. The holographic principle found support from an unexpected direction: string theory, the leading candidate for a theory of quantum gravity. String theorists discovered that certain theoretical constructs called anti-de Sitter spaces had holographic descriptions, that physics in the bulk of the space could be completely described by a theory living on its boundary. This ADS-CFT correspondence, developed by Juan Maldacena and others, provided the first concrete example of holography in physics. But even as the holographic principle gained theoretical support, new puzzles emerged. In 2012, Ahmed Almheri, Donald Marloff, Joseph Polchinski, and James Sully, collectively known as AMPS, published a paper that seemed to show that the holographic solution to the information paradox led to its own contradictions. The AMPS argument, dubbed the firewall paradox, suggested that any attempt to preserve information in black hole evaporation would require the existence of a firewall at the event horizon, a region of intense energy that would incinerate anything trying to cross it. This directly contradicted Einstein's equivalence principle, which states that someone falling through the event horizon should experience nothing unusual at the moment of crossing. The firewall paradox forced physicists to choose between three fundamental principles: information conservation, quantum mechanics; the equivalence principle, general relativity; and the assumption that physics outside the black hole appears normal to distant observers. It seemed impossible to maintain all three simultaneously. This new crisis in black hole physics sparked renewed interest in the information paradox. Conferences were organized, papers were published, and heated debates erupted across the theoretical physics community. Some physicists embraced firewalls as a radical but necessary revision of our understanding. Others searched for ways to avoid the paradox entirely. One of the most intriguing developments came from the realization that quantum mechanics might allow for phenomena even stranger than anyone had previously imagined. The concept of quantum error correction, borrowed from quantum computing, suggested that information might be preserved in black holes through redundant encoding across multiple degrees of freedom. Meanwhile, advances in quantum information theory revealed new ways that information could be hidden and recovered. The phenomenon of quantum entanglement, where particles become correlated in ways that seem to transcend space and time, offered new possibilities for understanding how information might escape from black holes through subtle quantum correlations.
Perhaps the most revolutionary idea to emerge from this period was the suggestion that the interior of a black hole might not exist at all in the conventional sense. Instead, what we interpret as the black hole interior might be an emergent description of quantum entanglement between particles outside the horizon. The smooth spacetime inside the black hole, according to this view, is a kind of collective illusion created by the quantum entanglement of Hawking radiation. This ER equals EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that Einstein-Rosen bridges, or wormholes, and Einstein-Podolsky-Rosen entanglement, or quantum correlation, are actually different descriptions of the same phenomenon. In this picture, the black hole interior is connected to the exterior not through space and time, but through quantum entanglement. As our understanding of the information paradox has evolved, it has become clear that resolving it will require new insights into the fundamental nature of space, time, and quantum mechanics. The paradox has already led to revolutionary ideas like the holographic principle, which have found applications far beyond black hole physics.
The debate continues to this day, with new proposals and counterarguments appearing regularly in the physics literature. Some researchers now suspect that the paradox cannot be resolved within our current theoretical frameworks, but will require a completely new understanding of quantum gravity, a theory that successfully unifies general relativity and quantum mechanics. What makes this quest so compelling is that it's not just an abstract mathematical puzzle. The information paradox touches on some of the deepest questions about the nature of reality. Is information truly fundamental? Are space and time emergent phenomena? What is the relationship between gravity and quantum mechanics? The search for answers has already transformed our understanding of physics in unexpected ways. The holographic principle has become a powerful tool for studying strongly coupled quantum systems. The ADS-CFT correspondence has provided new insights into condensed matter physics and quantum field theory. Concepts from black hole physics have found applications in quantum computing and quantum error correction. Perhaps most importantly, the information paradox has shown us that black holes are not just astrophysical curiosities, but laboratories for exploring the deepest principles of physics. They represent the ultimate testing ground for our theories about reality, places where the familiar laws of physics break down and new, stranger truths emerge. As we stand on the threshold of new discoveries, with gravitational wave astronomy revealing new populations of black holes, the Event Horizon Telescope promising ever more detailed images of event horizons, and quantum computers beginning to simulate black hole physics in the laboratory, the information paradox remains one of the greatest challenges in theoretical physics. Solving it may require insights that we can barely imagine today. But if history is any guide, the solution will not only resolve the paradox, but will open up entirely new vistas of understanding, revealing aspects of reality that we never suspected existed. The cosmic recyclers. As we approach the conclusion of our journey through the strange and wonderful world of black holes, it's time to consider their role in the grand story of cosmic evolution. Far from being mere endpoints of stellar death, black holes have emerged as key players in the ongoing drama of the universe, cosmic recyclers that shape the formation of galaxies, regulate star formation, and may even seed the formation of new structures across vast scales of space and time. This perspective on black holes as active participants in cosmic evolution is relatively recent. For decades after their theoretical prediction and observational discovery, black holes were viewed primarily as cosmic vacuum cleaners, objects that consumed matter and energy without giving anything back. The phrase black hole itself reinforces this image of a cosmic drain from which nothing can escape. But this picture began to change as astronomers developed more sophisticated observations of galaxies and their central black holes. What they discovered was a universe where black holes and galaxies grow together in a delicate cosmic dance, each influencing the other's development over billions of years. The story begins with the recognition that nearly every large galaxy harbors a supermassive black hole at its center. This isn't a coincidence, but reflects a deep connection between galactic and black hole evolution. As galaxies form and merge in the early universe,
Their central black holes grow by consuming gas and occasionally merging with each other. Somewhere in the universe, matter is crossing an event horizon for the first time, beginning a journey toward a singularity where the known laws of physics cease to apply. Information is being encoded in Hawking radiation in ways we don't yet understand. Space and time are being curved into geometries that challenge our deepest intuitions about reality. These processes unfold according to mathematical laws that human beings have painstakingly discovered over centuries of careful thought and observation. They connect us to the deepest principles that govern our universe. They remind us that we are part of something much larger and more mysterious than ourselves. The story of black holes teaches us that the universe is far stranger and more wonderful than we could have imagined. It shows us that reality extends far beyond the world of our everyday experience, into realms where time slows down, space curves back on itself, and the very nature of existence becomes questionable. But it also teaches us that this strange reality is not beyond human comprehension. Through patience, creativity, collaboration, and the careful application of reason, we can push back the boundaries of the unknown. We can transform mystery into understanding, speculation into knowledge, wonder into wisdom. The black holes that once existed only in the imagination of an 18th century priest are now observed by telescopes, detected by gravitational wave interferometers, and imaged by planet-spanning arrays of radio dishes. The mathematical singularities that once seemed like mere curiosities have become windows into the deepest structure of reality. What seemed impossible has become inevitable. What appeared absurd has proven profound. What looked like an ending has turned out to be a beginning. This is perhaps the most important lesson from our journey through the world of black holes. The universe is always more surprising, more beautiful, and more comprehensible than we expect. There are always new mysteries waiting to be discovered, new connections waiting to be made, new insights waiting to transform our understanding of reality. As you drift off to sleep, imagine the gravitational waves from distant black hole mergers passing through your room, stretching and compressing space by amounts smaller than the nucleus of an atom. Think about the supermassive black hole at the center of our own galaxy, 4 million times the mass of our Sun, quietly anchoring the stellar system that includes Earth. Consider the possibility that the very space around you might be holographic, that the information describing everything in your room might be encoded on its walls like a cosmic hologram. Ponder the question of whether the matter that makes up your body will someday fall into a black hole, and if so, whether the information that defines you will survive in some form. These are not idle philosophical speculations, but real questions at the frontier of human knowledge. They connect your existence to the deepest principles of physics, to the grandest structures in the cosmos, to the ongoing quest to understand reality itself. The story of black holes is still being written. New chapters are being added with each gravitational wave detection, each new image from the Event Horizon Telescope, each theoretical insight that brings us closer to understanding the information paradox. Future discoveries will undoubtedly surprise us, challenge us, and inspire us in ways we cannot yet imagine. But whatever those discoveries may bring, they will build on the foundation laid by centuries of human curiosity and ingenuity. They will extend the great conversation that began when John Mitchell first wondered whether light could be trapped by gravity, that continued when Einstein realized that space and time could be curved, that accelerated when Hawking discovered that black holes could evaporate. This conversation includes all of us. Every time we look up at the night sky and wonder about the universe beyond our small planet, we participate in the same quest for understanding that has driven the discovery of black holes. Every time we ask questions about the nature of reality, we join the same community of seekers that has pushed back the boundaries of the unknown. The universe is vast, ancient, and full of wonders we have yet to discover. Black holes are just one of these wonders, but they may be the key to understanding all the rest. In their event horizons, we glimpse the limits of space and time. In their singularities, we confront the breakdown of physical law. In their information paradoxes, we face questions about the fundamental nature of reality. These cosmic mysteries await future generations of explorers, scientists and philosophers, engineers and artists, all united by curiosity about the universe and our place in it. The tools they will use may be unimaginable to us today, just as the Event Horizon Telescope would have seemed like magic to John Mitchell. But the questions they pursue and the wonder that drives them will be the same that has motivated every generation of humans who have looked up at the stars and asked, "What's out there? How does it work? And how can we understand it?" Sweet dreams, fellow travelers in this cosmic journey. Tomorrow, the quest continues.
The information paradox remains unsolved. We still don't understand what happens to matter and information that falls past the event horizon. We don't know whether the interior of a black hole is a real place or an emergent description of quantum entanglement. We don't know how the first supermassive black holes formed so quickly in the early universe, or what role they played in creating the cosmic structures we see today. These mysteries are not failures of science, but invitations to deeper understanding. They represent the frontier of human knowledge, the edge of what we know and the beginning of what we might discover next. The history of black hole physics teaches us that our most profound insights often come from pursuing ideas that initially seem impossible or absurd. Who could have imagined, when John Mitchell first calculated the properties of his dark stars, that these objects would eventually become laboratories for testing the deepest principles of physics? Who could have predicted that the mathematical peculiarities in Einstein's field equations would lead to discoveries about the holographic nature of reality? Who could have foreseen that the search for gravitational waves would require building the most sensitive instruments ever constructed by human beings? The story of black holes is ultimately a story about the power of human curiosity and reasoning. It shows how we can use mathematics and careful observation to understand phenomena that are completely outside our direct experience. We have never visited a black hole, never touched its event horizon, never felt the crushing force of its gravity. Yet through the application of physical laws discovered in earthbound laboratories, we have learned to predict their properties with extraordinary precision. This process of discovery continues today. New generations of telescopes, from the James Webb Space Telescope to proposed gravitational wave detectors in space, promise to reveal new aspects of black hole physics. Quantum computers may eventually be able to simulate black hole formation and evaporation, providing new insights into the information paradox. Advances in theoretical physics may finally unite general relativity and quantum mechanics in a theory of quantum gravity. Each new discovery will undoubtedly raise new questions. This is the nature of scientific progress. Each answer reveals new puzzles. Each solved mystery opens doors to deeper mysteries. Black holes will likely continue to surprise us, challenge our assumptions, and force us to revise our understanding of reality. But there is something profoundly satisfying about the human quest to understand black holes, even if we never fully succeed. In reaching toward these cosmic extremes, we reach toward the limits of our own capabilities as thinking beings. We stretch our imagination, extend our mathematical tools, and push our technology to its very limits. In doing so, we discover not just new facts about the universe, but new aspects of ourselves. We learn that human beings can comprehend phenomena that span the entire history of the cosmos. We learn that our minds, evolved on a small planet orbiting an ordinary star, can grasp the deepest principles that govern reality on the largest scales. The story of black holes is also a reminder of how interconnected human knowledge really is. The same mathematical insights that describe the event horizon of a black hole also illuminate the behavior of quantum systems in condensed matter physics. The techniques developed to detect gravitational waves have applications in quantum sensing and precision measurement. The holographic principle, born from black hole physics, may revolutionize our understanding of quantum many-body systems. This interconnectedness extends beyond physics to philosophy, mathematics, computer science, and even art. Black holes have inspired countless works of science fiction, captured the imagination of artists and poets, and challenged philosophers to think about the nature of existence itself. They represent a meeting point of scientific rigor and cosmic wonder, of mathematical precision and poetic inspiration. As we settle into sleep tonight, we can take comfort in knowing that across the universe, the cosmic dance continues. Binary black holes spiral toward merger, sending gravitational waves rippling through space-time. Supermassive black holes feed at the centers of distant galaxies, powering quasars that outshine entire stellar populations.
event horizons mark boundaries where our understanding of space and time breaks down, where new physics waits to be discovered.
This process may help explain why heavy elements are found even in the most distant and earliest galaxies we can observe. The rapid growth of supermassive black holes in the early universe, followed by their energetic feedback, could have dispersed elements throughout space much faster than would be possible through stellar winds and supernovae alone. Recent observations with the James Webb Space Telescope have begun to reveal the crucial role that black holes played in the early universe. JWST can see further back in time than any previous instrument, observing galaxies as they appeared when the universe was only a few 100 million years old. Remarkably, these early galaxies already contain supermassive black holes, objects that seem almost impossibly massive given the young age of the universe. These observations suggest that supermassive black holes began forming very early in cosmic history, perhaps from the collapse of the first generation of stars or through other exotic formation mechanisms. Their rapid growth and energetic feedback may have been crucial in shaping the first galaxies and establishing the patterns of structure formation that persist to this day. Looking toward the future, black holes will continue to play important roles in cosmic evolution. As the universe ages and expands, star formation will gradually decline as gas becomes more dilute and less available for forming new stars. In this future cosmos, stellar mass black holes will become an increasingly important repository of matter. Eventually, in the far distant future when stars no longer shine and galaxies have merged into a few giant systems, supermassive black holes may be among the last sources of energy in the universe. Their slow evaporation through Hawking radiation will provide a trickle of energy that could, in principle, support the last vestiges of complexity in a universe heading toward maximum entropy. But that future is unimaginably distant, more than 10 to the 100 years from now. For the foreseeable future of cosmic evolution, black holes will continue to serve as engines of change, regulating star formation, redistributing matter and energy, and shaping the evolution of galaxies and larger structures. The recognition of black holes as cosmic recyclers, rather than mere consumers, represents a fundamental shift in our understanding of these objects. They are not destroyers, but transformers, cosmic engines that convert gravitational potential energy into radiation and motion, that regulate the growth of galaxies, that redistribute the elements necessary for life, and that may hold clues to the ultimate fate of information and energy in our universe. This perspective transforms our entire view of cosmic evolution. Rather than seeing black holes as exotic endpoints of stellar death, we now understand them as integral components of the cosmic ecosystem, objects whose presence and activity are necessary for the universe to evolve into the rich, complex, star-filled cosmos we observe today. The endless mystery. As we reach the end of our long journey through the history and physics of black holes, it's worth pausing to reflect on how far we have traveled, both literally across the cosmos and metaphorically through human understanding. We began with John Mitchell, a country priest in 18th century Yorkshire, imagining dark stars from which light could not escape. We end in the 21st century with images of actual black hole horizons and the detection of gravitational waves from black hole mergers billions of light years away. The journey spans nearly 2.5 centuries of human thought and discovery. It encompasses the work of some of the most brilliant minds in history, from Einstein to Hawking, from Chandrasekhar to the thousands of scientists who made LIGO and the Event Horizon Telescope possible. It represents triumph over seemingly impossible technical challenges, the resolution of conceptual puzzles that seemed beyond human comprehension, and the opening of entirely new windows on the universe. Yet for all we have learned, black holes remain fundamentally mysterious. They exist at the intersection of our most successful physical theories, general relativity and quantum mechanics, yet they reveal deep incompatibilities between these theories that we have not yet resolved. They challenge our most basic assumptions about space, time, information, and reality itself. But the relationship isn't one-sided. As supermassive black holes consume matter, they release enormous amounts of energy through their accretion disks and relativistic jets.
This energy heats the surrounding gas, sometimes to such high temperatures that it becomes too hot to form new stars. In this way, black holes can regulate star formation throughout their host galaxies. Picture a young galaxy in the early universe, rich in gas and dust, forming new stars at a prodigious rate. At its center, a growing supermassive black hole feeds on the available material, gradually becoming more and more luminous. Eventually, the energy output from the black hole's accretion disk becomes so intense that it begins to heat and disperse the galaxy's gas supply. Star formation slows, then stops entirely. The galaxy enters a quiescent phase, its stellar population aging without significant new additions. The central black hole, having consumed much of the available fuel, also becomes less active. This creates a balance. The galaxy can no longer feed its central black hole efficiently, and the black hole can no longer suppress star formation through its energetic output. This cycle of feeding and feedback helps explain one of the most important relationships in observational astronomy: the correlation between the mass of a galaxy's central black hole and the velocity dispersion of stars in its central bulge. Known as the M-sigma relation, this correlation suggests that black holes and galaxies regulate each other's growth over cosmic time. The relationship is remarkably tight. Galaxies with more massive central bulges invariably harbor more massive central black holes, and vice versa. The ratio is approximately 1 to 700. For every 700 solar masses in the galactic bulge, there's about 1 solar mass in the central black hole. This relationship holds across a vast range of galaxy types and sizes, from small elliptical galaxies to giant systems containing trillions of stars. But black holes influence cosmic evolution on scales much larger than individual galaxies. When supermassive black holes are actively feeding in their quasar phase, they can be seen across most of the observable universe. The energy they release can affect gas and star formation in neighboring galaxies, creating bubbles and cavities in the intergalactic medium that persist for hundreds of millions of years. Some of the most spectacular examples of black hole feedback can be seen in galaxy clusters, massive collections of hundreds or thousands of galaxies bound together by gravity. At the centers of these clusters, astronomers often find giant elliptical galaxies hosting some of the most massive black holes in the universe. The jets from these black holes can extend for millions of light years, creating enormous cavities in the hot gas that pervades the cluster. These jets don't just create holes in the gas, they also transport energy and magnetic fields across vast distances, influencing star formation and gas dynamics throughout the cluster. In some cases, the mechanical energy deposited by black hole jets can balance the cooling of cluster gas, preventing the formation of new stars and maintaining the cluster in a steady state for billions of years. The role of black holes in cosmic evolution becomes even more intriguing when we consider their relationship to dark matter, the mysterious substance that makes up about 85% of all matter in the universe. While black holes themselves are not dark matter, they may play crucial roles in shaping the distribution of dark matter halos that serve as the scaffolding for galaxy formation. Computer simulations of cosmic structure formation now routinely include models of black hole growth and feedback. These simulations show that without black hole feedback, galaxies would continue forming stars until they exhausted their gas supply, leading to a universe filled with red, dead galaxies much earlier than what we observe. The regulation provided by black holes helps maintain a population of actively star-forming galaxies throughout cosmic history. But perhaps the most remarkable aspect of black holes as cosmic recyclers is their role in redistributing the heavy elements that make planets and life possible. When massive stars explode as supernovae, they scatter elements like oxygen, silicon, and iron throughout space. But some of this material inevitably falls into black holes, where it might seem to be lost forever. However, black holes don't just consume. They also expel material through their powerful jets and winds. These outflows can carry heavy elements far from their point of origin, enriching gas clouds throughout galaxies and even in the intergalactic medium. In this way, black holes serve as cosmic distributors, spreading the elements necessary for planet formation and life across vast distances. The jets from supermassive black holes are particularly effective at this redistribution. Accelerated to near the speed of light by magnetic fields twisted around the black hole, these jets can transport material across millions of light years. When they finally slow down and dissipate, they deposit their cargo of heavy elements in distant regions where it can eventually be incorporated into new generations of stars and planets.
The cosmic web weavers. As we delve deeper into the role of black holes in cosmic evolution, a picture emerges of these objects not merely as consumers of matter and energy, but as architects of the largest structures in the universe. To understand this role, we must zoom out from individual galaxies to consider the cosmic web, the vast network of filaments and voids that organizes matter on the largest observable scales. Picture the universe as seen from a distance so vast that galaxies appear as mere points of light, like fireflies scattered across a summer evening. From this cosmic perspective, the distribution of matter is not random, but follows intricate patterns. Galaxies are organized into long, thin filaments that stretch across hundreds of millions of light years. These filaments meet at nodes where massive galaxy clusters form. Between the filaments lie vast voids, regions of space largely empty of galaxies, where the darkness is broken only by the occasional lonely stellar system. This cosmic web structure emerged from tiny quantum fluctuations in the density of matter in the early universe. These fluctuations, imprinted on the cosmic microwave background radiation that we can still observe today, served as seeds for the gravitational collapse that eventually formed all cosmic structures. Dark matter, that mysterious substance that makes up about 85% of all matter, played a crucial role in this process. Its gravitational influence helping to pull ordinary matter into the patterns we observe today. But what role did black holes play in shaping this cosmic architecture? The answer is complex and still being unraveled by astronomers and cosmologists, but it's becoming clear that black holes have been active participants in cosmic structure formation from very early times. The story begins with the formation of the first stars in the universe, perhaps 100 to 200 million years after the Big Bang. These primordial stars were very different from the stars we see today. Formed from gas that contained only hydrogen and helium, the heavy elements that make up planets and enable life had not yet been forged in stellar cores. They were likely much more massive than typical modern stars. When these first-generation stars died, many collapsed to form the first stellar mass black holes in cosmic history. But some may have formed even more massive black holes, perhaps hundreds or thousands of times the mass of our Sun, through direct gravitational collapse of massive gas clouds, or through the merger of multiple stellar mass black holes. These primordial black holes became the seeds around which the first galaxies formed. As gas flowed along the filaments of the cosmic web toward regions of high dark matter density, they encountered these early black holes, which began to grow by accretion. The energy released by this accretion process, often appearing as bright quasars, had profound effects on the surrounding environment. Picture the early universe as a cosmic construction site, with the first galaxies taking shape around these growing supermassive black holes. The energy output from accreting black holes heated the surrounding gas, sometimes preventing it from cooling and forming stars, sometimes triggering bursts of star formation through shock waves and turbulence. The balance between these effects helped to determine the ultimate size, shape, and properties of the galaxies that formed. But the influence of black holes extended far beyond individual galaxies. The most powerful quasars in the early universe could affect gas and star formation processes across vast distances. Their intense radiation and powerful jets could ionize hydrogen gas throughout large regions of space, contributing to a cosmic phase transition known as reionization that fundamentally changed the properties of intergalactic space. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that absorbed most forms of electromagnetic radiation. This dark age ended when the first stars and quasars began shining, their ultraviolet radiation ionizing the hydrogen and making the universe transparent to most wavelengths of light. Black holes, through their role in powering some of the brightest quasars in the early universe, were major contributors to this cosmic dawn. The reionization process had lasting effects on cosmic structure formation. Ionized gas behaves differently from neutral gas. It's hotter and more resistant to gravitational collapse. This affected the formation of small galaxies and may explain why the universe contains fewer dwarf galaxies than some theoretical models predict. Black holes, in other words, may have played a role in determining not just where galaxies formed, but how many formed and what sizes they achieved. As the universe evolved and galaxies grew through mergers and accretion, the supermassive black holes at their centers grew as well. Each time two galaxies merged, their central black holes eventually found each other and merged as well, creating even more massive black holes. These merger events, now detectable through gravitational wave astronomy, shaped the distribution of black hole masses we observe today. But galaxy mergers aren't random events. They're guided by the large-scale structure of the cosmic web. Galaxies tend to merge when they encounter each other along the filaments of the web, or when they fall into massive galaxy clusters at the intersections of filaments. This means that the growth of supermassive black holes has been intimately connected to the cosmic web structure from the beginning. The feedback from growing black holes, in turn, has shaped the evolution of the cosmic web itself. When supermassive black holes are actively accreting matter in their quasar phase, they can launch jets of particles and radiation that extend far beyond their host galaxies. These jets deposit energy and momentum into the intergalactic medium, affecting the flow of gas along cosmic web filaments and potentially redirecting matter toward or away from other galaxies. Some of the most spectacular examples of this process can be seen in galaxy clusters, where the central supermassive black holes create enormous bubbles and cavities in the hot X-ray emitting gas that pervades these systems. These bubbles can be hundreds of thousands of light-years across and persist for hundreds of millions of years, representing a significant fraction of a galaxy cluster's lifetime. The energy required to create these structures is staggering, equivalent to the explosion of millions of supernovae. Yet this energy is delivered relatively gently over millions of years through the steady pressure of relativistic jets rather than through sudden violent explosions. This allows the black hole feedback to regulate gas cooling and star formation throughout the cluster without completely disrupting the system. Recent observations with advanced X-ray telescopes have revealed that this black hole feedback is remarkably common in galaxy clusters. Nearly every massive cluster shows evidence of bubbles, jets, or other signatures of central black hole activity. This suggests that supermassive black holes play a fundamental role in regulating the growth and evolution of the largest gravitationally bound structures in the universe.
The influence of black holes on cosmic structure extends to even larger scales through their role in cosmic rays, high-energy particles that travel through intergalactic space at nearly the speed of light. Many of these cosmic rays are thought to originate from the jets of supermassive black holes, accelerated to extreme energies by the powerful magnetic fields that thread these outflows. These cosmic rays carry energy and momentum across vast distances, potentially affecting star formation and gas dynamics in galaxies far from their point of origin. They also contribute to the heating of the intergalactic medium, affecting how gas flows along cosmic web filaments and affecting the rate at which galaxies can accrete new material for star formation. The relationship between black holes and cosmic structure formation is further complicated by the role of dark matter. While black holes themselves are made of ordinary matter, they're embedded within dark matter halos that provide the gravitational scaffolding for galaxy formation. The properties of these dark matter halos, their mass, concentration, and merger history, influence how supermassive black holes grow and how their feedback affects their surroundings.
Quantum information revolution. As we venture deeper into the 21st century, the intersection of black hole physics and quantum information theory is giving birth to a new understanding of reality itself. This revolution began with the recognition that information, not matter, not energy, but pure information, might be the most fundamental constituent of the universe. Black holes, those cosmic extremes where our understanding breaks down, have become the laboratories where this new paradigm is being tested and refined. The story of this quantum information revolution began with a curious observation made by Jacob Bekenstein in the early 1970s. Bekenstein, a graduate student at Princeton University, was troubled by the apparent violation of the second law of thermodynamics that seemed to occur when matter fell into a black hole. The second law of thermodynamics states that the entropy, roughly speaking the amount of disorder, in any closed system must always increase or stay the same, never decrease. But when a hot object falls into a black hole, its entropy seems to simply vanish from the observable universe. This appeared to violate one of the most fundamental principles in physics. Bekenstein proposed a radical solution. Black holes themselves must have entropy, and this entropy must increase whenever matter falls in. But where could this entropy be located? The interior of a black hole is hidden from outside observation, and the event horizon is supposedly just a mathematical boundary with no physical substance. Bekenstein made a bold suggestion. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This was a startling departure from ordinary thermodynamics, where entropy typically scales with volume. A black hole's entropy, Bekenstein proposed, was given by 1/4 of its surface area measured in units of the Planck length squared. When Stephen Hawking discovered that black holes emit thermal radiation, he provided the missing piece of Bekenstein's puzzle. The temperature of this radiation was exactly what would be expected if the black hole had the entropy that Bekenstein had calculated. The Bekenstein-Hawking entropy formula became one of the most important relationships in theoretical physics, connecting gravity, quantum mechanics, and thermodynamics in a single elegant equation. But the implications of this formula extended far beyond black hole physics. If a black hole's entropy is proportional to the area of its boundary rather than its volume, this suggested that all the information about the black hole's interior is somehow encoded on its two-dimensional surface. This was the birth of the holographic principle, the idea that everything you perceive is three-dimensional reality. Every object in your room, every atom in your body, every thought in your mind is actually a projection from information stored on a distant two-dimensional surface, like a cosmic hologram.
This isn't just a metaphor, but a serious proposal about the fundamental nature of space, time, and reality itself. The holographic principle gained concrete mathematical form through the ADS-CFT correspondence discovered by Juan Maldacena in 1997. This correspondence showed that certain theories of quantum gravity in a curved space called anti-de Sitter space were exactly equivalent to quantum field theories living on the boundary of that space. It was the first concrete example of holographic duality in physics, providing a mathematical framework for understanding how three-dimensional physics could emerge from two-dimensional information. But the full implications of the holographic principle for black holes and quantum information remained unclear. How exactly is information encoded on the event horizon? How does this encoding change as the black hole evaporates? And most importantly, how can information escape from a black hole without violating the fundamental principles of quantum mechanics? These questions took on new urgency with the development of quantum computing and quantum information theory in the 1990s and 2000s. As physicists learned to manipulate individual quantum systems and study the flow of quantum information, they began to recognize that information might be more fundamental than matter or energy. In the quantum world, information has physical consequences. It can be processed, transmitted, and stored in ways that have no classical analog. Quantum information is qualitatively different from classical information. While classical information can always be copied, quantum information cannot be duplicated due to the no-cloning theorem. While classical information can be read without disturbing it, measuring quantum information necessarily changes it. These unique properties of quantum information provide new tools for understanding the black hole information paradox. One of the most important developments came from the recognition that quantum error correction, a technique developed for protecting quantum information in quantum computers, might also operate in black holes. In quantum error correction, information is encoded redundantly across multiple quantum systems so that it can be recovered even if some of the systems are damaged or lost. Applied to black holes, this suggests that information falling past the event horizon might be encoded redundantly in the quantum state of the black hole and its surroundings. Even though some of this information appears to be lost inside the black hole, enough might remain accessible to outside observers to allow complete reconstruction of what fell in. But understanding exactly how this quantum error correction might work in black holes required new mathematical tools and conceptual frameworks. Physicists began to study the properties of highly entangled quantum systems, systems where many particles are correlated in complex ways that transcend ordinary space and time. These studies revealed phenomena that seemed to blur the boundaries between information and geometry, between quantum mechanics and gravity. In certain highly entangled states, the quantum correlations between particles can create effective geometries that look like curved space-times. The connectivity of space itself might emerge from the pattern of quantum entanglement between the fundamental constituents of reality. This led to the remarkable proposal that space-time itself might be constructed from quantum entanglement. In this picture, the smooth geometry of Einstein's general relativity is not fundamental, but emerges from underlying quantum information processing on the most fundamental level. The curvature of spacetime, the gravitational force, and even the existence of space and time themselves might be consequences of the way quantum information is organized and processed on the most fundamental level. The connection between entanglement and geometry was made concrete through the ER equals EPR conjecture, which proposed that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement are actually different descriptions of the same phenomenon. When two quantum systems become maximally entangled, they create a wormhole connecting them through the geometry of spacetime. This applied to black holes suggests that the event horizon might not be a boundary in the conventional sense, but rather one end of a wormhole connecting the black hole's interior to the exterior universe. Information falling into the black hole would travel through this quantum wormhole, emerging in the Hawking radiation in a highly scrambled but ultimately recoverable form. This picture has profound implications for our understanding of causality and the nature of space and time. If distant regions of space can be connected through quantum entanglement, then the locality of physics, the idea that objects can only be directly influenced by their immediate surroundings, might need to be fundamentally revised. The universe might be far more interconnected than our everyday experience suggests, with quantum correlations creating hidden connections across vast distances. Recent developments in quantum simulation and quantum computing have begun to provide experimental tests of these ideas. Physicists can now create and manipulate highly entangled quantum systems in the laboratory, studying how quantum information flows through them and how entanglement patterns give rise to emergent phenomena that resemble gravity and curved spacetime. In 2019, researchers at Google claimed to have achieved quantum supremacy, performing a calculation on a quantum computer that would be practically impossible on any classical computer. While the specific calculation they performed was somewhat artificial, the achievement demonstrated that quantum information processing had reached a new level of sophistication. More importantly, it showed that quantum computers might be soon powerful enough to simulate black hole physics directly, providing new insights into the information paradox and other deep questions in quantum gravity. Other research groups have used quantum simulators, systems of cold atoms or trapped ions that can be programmed to mimic the behavior of other quantum systems, to study simplified models of black hole evaporation. These experiments have revealed new phenomena, such as the many-body localization that can prevent information from escaping even in highly entangled systems, providing new perspectives on how information might be trapped and released in black holes. Perhaps most remarkably, recent theoretical work has suggested that the process of quantum error correction in black holes might be observable in principle.